Hello everyone. In the previous lecture, we already discussed the completeness property, which is very important. It is essentially the property that separates the set of real numbers from the set of rational numbers. And the completeness property is based on the notion of the supremum and infimum of a set. Today, we're going to discuss several applications of the completeness property. The first application here is the following. It says that supremum and infimum are compatible with algebraic properties of the set R, the set of real numbers. So what does it mean to be compatible? Well, the compatibility is illustrated by the following lemma. Say that let A be a real number. The set capital S is a subset of the set of real numbers and it is bounded above. We define A plus S to be the set of all summation A plus S for this small letter S being an element in this set capital S. Then the supremum of this set A plus S exactly equal to A plus the supremum of the set S. In other words, this lemma says that we can take the supremum and addition in a compatible way. We take the supremum of an addition and that's going to be equal to the addition of the supremums. That's why it is said that supremum and infimum are compatible with algebraic properties of the set R. And this lemma is important, but we're gonna skip its proof and we're gonna discuss other application of the completeness property. The next thing is the notion of supremum and infimum can be defined for functions. How do we do that? Let's consider a function f from some set D to the set of real numbers. Then the infimum of this function f is defined to be the infimum of the following set. Excuse me. We look at the image of the whole domain D under the function f. That is a subset of the set of real numbers. Then we take the infimum of this subset. That's going to be the infimum of the function. A priori, the infimum might not exist, but we can always give a definition. Similarly, we can define the supremum of a function to be the supremum of the set of the range of this function. Again, we consider f of D the image of the whole domain D under the function f. This is also called the range of the function. So, in short, the infimum and supremum of a function are just the infimum and supremum of the set, which is the range of this function. Using this definition, you can derive natural properties, uh, infimum and supremum for function. Now, the next application of the completeness property is called the Archimedean property, and this is actually a very, very important statement that you're gonna see again and again in this class. So basically, in this class, in many situations, when you need the completeness property, you actually gonna use this consequence of the completeness property, namely this Archimedean property. That's why you see these statements again and again in this class. So what is how does it so what is this statement? The statement says that the set n, remember n here is a set of all natural numbers. The set n here by the Archimedean property, the set n is not bounded above. Let me give proof to illustrate how the completeness property is used to obtain this Archimedean property. Again, the proof here is by contradiction. As I said in the previous lecture, proof by contradiction is a very important technique that you're going to see again and again in this class. Basically, you want to prove something is true, you assume that it's false. Then you deduce statements after statements until you get a contradiction. Because of the contradiction, the original assumption that the statement is false must not be true. That's why the statement is true. So here we assume that n is bounded above. Then by the definition of bounded above, n has an upper bound. Then by the completeness property, n has a supremum. Remember, the completeness property says that any set which has any set of real numbers which has an upper bound must have a supremum, which is a real number. This supremum might not be in the set, but it must be in the set of real numbers. Now, let's say n has a supremum and we call it u. Then by the order property that we discussed earlier, u minus 1 must be smaller than u. Now, u is the supremum. Remember, the supremum is the smallest upper bound, and you have a number which is smaller than that smallest upper bound. Then that smaller number cannot be an upper bound. That is, u minus 1 is not an upper bound. Consequently, there is some natural number n in the set of all natural number capital N, such that u minus 1 here must be smaller than n. And this is because of the definition of an upper bound. U minus 1 is not an upper bound. That means there must be some number in the set which is bigger than this number. And to call that number small letter n. Using the order property again, we deduce that u here is smaller than n plus 1. Now, the key observation is that n is a natural number. That's why n plus 1 is also a natural number. Why? Because the set of natural number is defined exactly in this way. Remember, the set of natural number defined as the summation of several copies of one of the element 1. We add two copies of element 1 together and obtain element code 2, and so on. And each step you add another copy of 1 to obtain another natural number. That's why in this case, n plus 1 must be a natural number. But this is a contradiction because u is supposed to be the upper bound. But here, u is smaller than a natural number, smaller than an element in this set. That's why not an upper bound. That's why we arrive at a contradiction. As soon as you arrive at the contradiction, the original assumption must be false. And that's why n must be bounded above, must not be bounded above. Now the corollary to the Archimedean property is also very important. It says that the infimum of the set of all reciprocals of the natural numbers, all numbers of the form 1 over n for n a natural number, this set has an infimum, and the infimum is actually equal to 0. Again, I would like to give a proof here because we didn't give any proof about the infimum notion yet. Obviously, this set has a lower bound. 0 is a lower bound. Any natural number is a positive number. That's why 1 over n is always bigger than 0. That's why 0 is a lower bound. Now, by the completeness property, this set has an infimum, and let X be the infimum of this set. So X is the greatest lower bound, and any other lower bound is smaller than or equal to X. As we mentioned earlier, since n is greater than 0, 1 over n is greater than 0. So 0 is a lower bound for this set. That's why 0 must be smaller than or equal to this number x, which, remember, is the greatest lower bound. Now, let's assume that x is bigger, strictly bigger than 0. We will show some contradiction. Again, proof by contradiction. So we have 0 smaller than x, smaller than or equal to 1 over n for any number, for any natural number n. By the order property, we deduce that nx is smaller than or equal to 1. Therefore, 1 over x is an upper bound for n. Why? Because in this case, by the order property, we have that n here is smaller than equal to 1 over x. This step is possible because x is a number bigger than 0 by our previous assumption. That's why 1 over x is upper bound. But remember, the set of all natural numbers doesn't have any upper bound. That is the Archimedean property. So the statement we just arrived here, we just obtained here, is a contradiction to the Archimedean property. That's why the assumption that x greater than 0 must be false, since 0 must be smaller than or equal to x, and x is not bigger than 0. Therefore, x must be equal to 0. So again, this is a very, very important statement that you're going to see again and again in class. It says that the infimum for all reciprocals of a natural number must be equal to 0. There are several corollaries we can deduce from that statement. The first one says that if t is any number greater than 0, then there exists a number called n depending on t, which is an element of the set of natural numbers such that 0 is smaller than the reciprocal of 1 over n and smaller than t. That is, for any number t bigger than 0, we can always find a reciprocal of a natural number which is in between 0 and t. The second corollary says that if y is bigger than 0, then there exists a number n, again, possibly depending on y, which is an element in the set of all natural numbers such that n y minus 1 is smaller than y, smaller than equal to y, and y is smaller than equal to ny. So this statement says that for any real number y, you can find consecutive natural numbers that y is sandwiched between these consecutive natural numbers. Now, the next application of the completeness property is about the existence of square root. Remember, in a previous lecture, we discussed the set Q of all rational numbers. We say that Q satisfies all algebraic and order properties just like the set of real numbers. However, there is no element in this set of all rational numbers Q such that the square of that element is equal to 2. And that is exactly an indicator of why Q is not the same as are the set of all natural numbers. So the set of all rational numbers is not the same as the set of all real numbers. That is, the set of all real numbers have some numbers which do not belong to a set of rational numbers. Today, we can make that statement rigorous. We can show that there exists a number, a real number, such that r squared is equal to 2. The proof here is a little bit long, so we're not going to discuss in this video. However, you can read it in the note or in the textbook. The key idea here is that the number r we are looking for here exactly equal to the supremum of the set S And the set S here is defined as the set of all real numbers such that zero smaller than x squared smaller than 2. Well, just to be consistent with the proof I'm giving here, I'm gonna make the slide modification here. So S here is set of all real numbers such that first is positive and second, the square of that number is smaller than 2. So this is the key idea. So let me emphasize by a color. Basically, we show the existence of a square root by a direct application of the completeness property. That is, the square root is actually the supremum of a y chosen set. You can read the proof with details in the note here. The corollary here is that actually this is true for any positive numbers, not just 2, but any positive number A. There is a unique number B such that B squared equal to A. So unique number here to make the statement correct. Here we need the qualification condition. This is unique zero smaller than B such that B squared equal to A. Now another application of the completeness property is about the density of rational numbers. Earlier, I just mentioned that the set of all rational numbers is a proper subset of the set of real numbers. That is, the set of real numbers has several more numbers than the set of rational numbers. In other words, that there are many holes in the set of rational numbers if we visualize them at points on a real line. Nevertheless, the statements we're going to see here show that even though the set of rational number is a proper smaller subset of the set of real numbers, it is actually everywhere. The theorem says that if x is smaller than y, then there exists a rational number r in the set of all rational numbers capital Q such that x is smaller than r smaller than y. That is, the set of rational numbers is dense in the set of all real numbers. If you just pick any two real numbers, there must be a rational number in between these two real numbers. That's what it means to say that the rational numbers are everywhere on the set of all real numbers. Pick any two numbers, then there's going to be a rational number in between these two numbers. It doesn't matter how small you choose the distance between these two numbers. There's always several rational numbers inside in between these two numbers. Similarly, if you choose any two numbers x and y, their there is also an irrational number in between these two numbers. So the set of irrational numbers is also dense in the set of real numbers. So that's it for today. And in the next lecture, we'll discuss intervals and several of its properties.